So, after long last, we come to a section that a lot of you must have been waiting for, and that is a section on convolutional neural networks, or as in some places, convolution neural networks, basically CNN, which is the deep learning for images. So just remember, convolutional or convolution neural networks, CNN, is a set of techniques that we only use for carrying out the classification of imagery data. So this is not something we would use for a regression problem, for instance. So if you have image data or imagery type data like the fashion CSV that we have been working with, which are essentially imagery type data, then convolutional neural networks are a good bet. So this is what are convolutional neural networks? If you are interested in deep learning, you must have heard of them. So I'm not going to go into the details of what all of this stuff is, but it is a set of very powerful deep learning techniques which can help identify and differentiate between dogs and cats. So here we have a dog and here we have a cat, and essentially we can train algorithms to differentiate between these two. And as you can see, different items, things like cars, horses, person, dog, they were also differentiated from each other with a very high level of accuracy. So basically, CNN are deep neural networks for images on steroids and coffee, because they are that powerful. That is why I say they are deep neural networks on steroids. And if we use MXNet, which we are going to use MXNet, then it is going to be a case of having deep neural networks on both steroids and coffee. So what is the big deal about building an algorithm or algorithms to classify images? Now, for human beings, this is no big deal. We have been doing image classification since birth. So maybe you've seen 6-month-old babies gurgling at their parents, and that is a form of image classification or image identification, because even as infants or babies, we can see and recognize our mothers. So human beings can easily distinguish between different objects. So here, this is a very detailed photo. Over here, right away, without any training, you can see that this is underwater photography. Over here we have corals. This is the deep ocean, another coral, and we can see a prawn, and maybe the prawn is not very happy to see us, but we can see it's a prawn with nice big tentacles and whatnot. So as human beings, we can do it straight off the bat. We can quickly recognize patterns, generalize from prior knowledge. So maybe as a young child, I saw what a prawn looked like. So right away, straight away, I can tell you that this is a prawn. And even if you don't know what a prawn looks like, now you know what a prawn is. And in future, you will be able to look at a similar prawn and say, hey, it's a prawn, and adapt to different image environments. However, things like computers or computer-powered objects such as drone need to be trained to differentiate between different objects and maybe recognize visual patterns. So CNN are biologically inspired variants of MLPs, and they try to mimic the visual cortex of the eye in order to carry out the kind of fine-scale classifications that we saw CNN can do for us. So the basis of CNN architecture is that it makes an explicit assumption that the inputs are images. So in case of CNN neural networks, as we are going to discover later on in the section, there's absolutely no compulsion to first extract all the pixels from your images. Indeed, we can feed images straight into our algorithm because CNN is prepared to accept inputs as images, and regular artificial neural networks and deep learning networks, they're not that effective with images, and especially with larger images. And now, unlike these two, CNNs are based on having the neurons arranged in a 3D form. So this is the architecture of an ordinary deep neural network. So here we have two hidden layers, and with two hidden layers we know that this is DNN. But in the case of CNN, you can see that the neurons are arranged in a 3D form, which means that they have width, they have height, and they have depth, and that is what makes them such a good candidate for accepting images as inputs. So this is the example of a CNN architecture. In addition to having a fully connected layer, which we also have in deep neural networks and artificial neural networks, CNN have something known as a convolution layer and a pooling layer. I am going to introduce you to these terms very shortly, but as you can see, we have worked with fully connected layers, and when we have two or more of these, we have a deep neural network. So indeed, a convolution neural network will also have fully connected layers, but before that, we are going to have steps to carry out things like convolution and pooling, and through these layers, so this is how the process moves. It literally moves on the assembly line. Through these layers, we perform the following functions related to image classification: convolution, nonlinearity or ReLU, that is why we say ReLU, pooling or subsampling, so here we carried out pooling, subsampling, classification through the fully connected layer. So every time we do classification, it is going to be through a connected layer, as we have seen before, but we carry out all of these steps prior to the classification step, which makes CNNs very powerful. So the step 1 is convolution. So the convolution step extracts features from the input image. So this is an input image. It's a nice input image. The convolution process preserves the spatial relationship between pixels by extracting features using small squares of input data. So essentially, we are going to extract features literally a small square by small square. So imagine we have an image 32 by 32 by 3 array of pixel values. The convolution layer is a flashlight. So this is like a flashlight. This is your convolution layer that shines over the top of the image, say, and it will cover 5x5 area. Now this flashlight is called a filter or a neuron or a kernel, and it is an array of numbers, and this region where it lands is a receptive field. So as the filter slides, so this particular filter or neuron, it won't stay here, then the receptive field will move here, then here, then here. So that is known as convolving. The filter is sliding or convolving. It multiplies the values in the filter with the original pixel values. So we carry out element wise multiplication all throughout using this particular filter or neuron, which might be a 5x5 array or a 3x3 array. I'm not going to discuss the mathematics in this. I just want you to understand what these terms are so that you are acquainted with the background of CNNs. So what we get after this is a feature map, which means that basically in a convolution neural network, we looked at an image through a smaller window or filter with the view of extracting features. So here we put a flashlight here, and then we got features, and then the features that we get are stored in a feature map like so. So we are going to actually have a feature map like this when we convolve over an image. After that, we move to the step of nonlinearity or ReLU, and this is used after the convolution operation. It is an element-wise operation. It is applied per pixel and replaces all the negative values in the feature, and it introduces non-linearity in our convolution neural network, because essentially in real world we basically have non-linearity. We can use other activation functions like tan hyperbolic or sigmoid, but ReLU is the recommended one, so that is what we will stick to. After that comes pooling. Now spatial pooling or subsampling reduces the dimensionality of each feature map, but it retains the most important information. So in the pooling step, we are carrying out dimensionality reduction. So remember, this is our rectified feature map. We have carried out convolution on it, we have implemented ReLU on it, and now with pooling, we are actually going to reduce its dimensionality to this size. So here's the input image. We do convolution, ReLU. We have the rectified features maps, and on that we apply pooling separately on each feature map to basically carry out data reduction. And finally we come to the fully connected layer. Now fully connected layer is a traditional multi-layer perceptron. It uses the softmax activation function in the output layer. We can use other activation functions, but softmax is the best activation function, so that will always be used in the output of the fully connected layers. And what we did in the previous step, so here we have two fully connected layers with softmax as the activation function, where we do the actual classification, and this is no different from what we did in the artificial neural networks or the deep neural networks. The only difference is that before coming on to this step, we did things like convolution and pooling, and we represented the high level features of the input image, and these high level features in turn are used for classification, and that is what makes convolution neural networks so powerful. And now we are going to actually learn to implement these using MXNet.